Alrighty guys, so tonight we're going to be talking about electron configuration. And so what that is going to be doing is building off of what we talked about yesterday about electron orbitals and atomic orbitals. And building off of that and going a little bit into more detail into how these orbitals are filled. So we know that electrons can be described by 4 quantum numbers, and that these quantum numbers occur in a very specific pattern that follows 3 rules. And that quantum numbers, you know this, describe the electron, including the type of orbitals involved, as well as their energy level and specific locations and spin. And just as a reminder, s orbitals are filled with 2 electrons, p orbitals are filled with a total of 6 electrons, d orbitals are filled with 10, and f orbitals have a total of 14 electrons. So those are some things that you knew already and to keep in mind. And we're going to learn about the 3 rules for filling electron orbitals. The first one is the Aufbau Principle. And this one is a principle that describes how electrons are added to orbitals one at a time. And so you build up orbitals as we proceed from atom to atom. And so you only add electrons one at a time, and then you build up the number of orbitals that you have as you add electrons, which means that you're adding protons, which means that we're going up from element to element. The next rule would be, you can go back if you want to and pause on the Aufbau Principle, but the next rule is Hund's rule, and this states that every orbital in a subshell will be occupied by 1 electron before any orbital is doubly occupied, meaning spin paired. So if you're trying to add electrons to a p orbital, for example, where there are 3 different orbitals, you cannot spin pair. You can't put 2 electrons in the same orbital before you've filled up the other 3 orbitals with 1 electron. And so all electrons in a singularly occupied orbitals have the same spin, and then you spin pair them. So you can pause and write that down if you'd like. And finally, we have the Pauli Exclusion Principle, or the Pauli Exclusionary Principle. And this is the rule that governs the fact that no 2 electrons can have the same 4 quantum numbers. What this means is that any 2 electrons found in the same orbital must therefore be spin paired, so that the 4th quantum number, which is spin, is not the same. So when we say spin paired, we mean 1 up, 1 spin up, 1 spin down. Okay, you might want to pause and write those 3 rules down. So what that means is that when determining what an element's electron configuration looks like, you have to take into account the Aufbau Principle, the Hund's rule, and the Pauli Exclusionary Principle, and begin filling orbitals starting at the 1s. And so as we fill, we can only fill 1 orbital at a time. You can't spin pair before you've filled up all the orbitals, and we build upon this starting at the 1s orbital. Okay, let's try and see what that looks like. So there's actually a pattern to filling up these orbitals, and I'm going to show you the pattern, and then I'm actually going to show you how you can see it from the periodic table so you don't have to measure anything. But the pattern is going from n equals 1 all the way to n equals 7, and you start out with an s. And then at the 2nd level you add a p. And then at the 3rd level you add a d, and at the 4th energy level you add an s type of orbital. So we start out at a 1s, and then a 2s, then a 2p, then a 3s, then a 3p, and so on and so on. And so you start adding different types of orbitals as you increase in energy level, but we actually fill them in a very specific order, and that's where these arrows are going. So we actually fill them following the arrows. So if you look, we would fill the 1s first. So I'm going to try and mark this up. So we would go 1s, then we would go 2s, and then we would go 2p, 3s, and I'm just going to, I'll write this down in a second. Then after the 3s, we would go 3p, 4s, then 3d, then back to 4p, then 5s, then 4d, 5p, 6s, should be a full arrow, then 4f, 5d, 6p, and 7s. Okay, so what that looks like, if you write it all down, is you go 1s, then 2s, then 2p, then 3s, then 3p, then 4s, back to 3d, then 4p, then 5s, then 4d, then 5p, then 6s, and so on and so on and so on. Okay? So you can draw your own arrows, and I would write that out. But that is a way to remember, and so you don't have to actually memorize this order. You can just write down those values. 91 to erase. Okay. So this pattern also, you can add the electrons to it. So we remember that an s orbital contains 2 electrons. So we start out with a 1s2, then a 2s2, and a p orbital can contain up to 6 electrons. So then we have a 2p6, then a 3s2, 3p6, 4s2, 3d. D has 5 orbitals, so you can contain 10 electrons. 4p6, 5s2, 4d10, 5p6, 6s2, 4f14, because it has 7 orbitals, 5d10, 6p6, and 7s2. So when you actually start filling that up, you can actually, we can take that pattern that we had and kind of draw it out with orbitals and fill those orbitals one at a time. And so if we do that, if we fill in those orbitals, it's going to remember, we add 1 electron at a time before we spin pair. So we're going to start out at the 1s, and we're going to do 1 spin up, then 1 electron spin down. Now that we've filled that energy level, we can go up to the 2s. And so now we can do 1 up, 1 down. And now we go to the 2p, because we're still on the same energy level, but we need to fill all the orbitals at that energy level, n equals 2, which has an s and a p orbital. And so we're going to do spin up, and before we can do spin down, we're actually going to do another spin up in that second orbital, and then a spin up in the third orbital before adding our paired spin downs. Then we move on to the 1s, the 3p, the 4s, the 3d, and so on and so on. And you can see as I go that I'm just putting 1 electron in each orbital before I spin pair them, and I'm not skipping any orbitals until everything is full. Okay. So this is kind of an electron configuration or orbital notation, if you might want to call it, where we're looking at the different orbitals and how those electrons are spin pairing and filling. Now the periodic table actually can be broken into orbital blocks. And so you have groups 1 and 2 are an s block, and remember that helium technically belongs next to hydrogen above group 2, but it doesn't behave like group 2, it behaves like group 8 because it's a noble gas. But just remember, for the purposes of electron configuration, it's part of the s block. Then our right side would be our p block, the middle side with our transition metals is our d block, and the detached lanthanides and actinides are our f block. And this can be further explained by adding the following multipliers to determine what the quantum number will be for each orbital group, and it actually helps to explain why it goes from 3p to 4s, then back to 3d. And so if you look here, if n is that period number, so 1 through 7, s orbitals, it's just a multiplier of n. P orbitals, it's a multiplier of n. For d orbitals, it's n minus 1. And for f orbitals, it's n minus 2. So if we actually added some n values or some periods, if I look up here, if I start at my 3s, I'm going to go through 3s and go all the way to 3p, right? I create that solid line. From 3p, if I add 1 more electron, I drop down to 4, and I'm going to pause here for a second. So after we go from the 3p, because remember, we fill the electrons going across the periodic table. So we go from 3s to 3p. And then we're going to go back down here and go to the 4s. But now on this level, the 4th energy level, it's now n minus 1 for d. So this then becomes 4 minus 1, which is 3d, and then back to 4p. So that kind of explains why. So we go 3s, 3p, then 4s, then 3d, then back to 4p. So we're still going in a line. We're not doing anything different. It's just that the multipliers are slightly different. Now, the 3d and 4s orbitals can sometimes be tricky. some special circumstances occur when we're trying to fill them, and it sometimes explains why the 4s orbital is filled prior to the 3d orbital. So if you've got energy increasing like here, and we start out at the 1s orbital, then we go to the 2s, and the 2p is slightly higher than that, then the 3s, which is higher than the 2p, the 3p is higher than the 3s, and then you have 3d. But if you look over here at 4s, it's actually slightly lower in energy than 3d, which is then slightly lower in energy than 4p, which is why it goes that way. But occasionally, if there should be 9 electrons or 4 electrons in the 3d level, the 4s sometimes actually gives up an electron because it was filled first, so that you can have either a fully filled or a partially filled 3d orbital. And the reason it does this is because a partially filled or fully filled 3d orbital is more stable than a not quite partially filled or not quite fully filled 3d and a 4s. And so it's actually something to do with more to have the symmetry of the 5 or 10 electrons rather than the 4 or 9, and it's all about kind of giving up and weighing in what is more stable and what costs less energy. So let's look at an example. So if we have copper with 29 electrons versus nickel with 28 electrons. Now, if you've got all the orbitals here, so we've got 28 versus 29, and I'm sorry about that electron, I don't know where that came from. If we start filling them up, we'll start with copper. We're going to go spin up, spin down. So that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29. Okay, so we are one shy of a full orbital right here, and we've got a full 4s orbital that was filled before the 3d. Now what's going to happen is that the 4s gives up that electron and donates it to the 3d to create this really stable 3d, which ends up costing less energy. Now if we look at nickel, if we fill it, so we go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28. Now, in order to fulfill this, we'd have to have the 4s donate both electrons, which is not energetically efficient. And so it is, in fact, too far away from symmetry for it to be worth the energy to donate that 4s. So the key here is that the energy costs and the gains that are created from the most stable atoms. So it costs energy to bump this electron up here, but the energy gain from the stability of this full 3d orbital is worth it. So just something to think about. If we look at chromium versus vanadium, so if we look at chromium, I don't know how I keep missing electrons, guys. We've got 24 electrons to worry about. So 1, 2, so I'm going to do them by twos. 2, 4, 6, 7, 8, 9, 10. And then we fill the 3s, then the 3p. Okay, so now we're at 2, 4, 6, 8, 10, 12, 14, 16, 18. That's going to give us 20. And then we get 21, 22, 23, 24, 25. Oh, man alive. So at 24, we don't have this electron there. And the electron is, in fact, in the 4s. So I'm going to draw a squiggle mark over this because it's not here. Okay, so with 24 electrons, you're looking at this. And this is only one electron away from that partially filled 3d orbital. And so the chromium will donate that 4s electron. It'll donate that 4s electron, and that 4s will go to the 3d and fill in that level. Okay? Now, it only does that because partially filled is also more stable than unpartially filled. But there's a balance cost to gain balance, kind of, if you think about economics. But if we look at vanadium that only has 23, if we fill that one, sorry, we've got 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 21, 22, 23. That, again, too much energy cost to fill in these. We're too far away from being partially filled. It's really one electron difference that makes it beneficial. So, I would like you guys to take a minute and find the electron configuration of magnesium. And so I want you to pause and on a scratch piece of paper or something, fill in the orbitals, or the electron orbitals of the electron configuration for magnesium. And then press play and we'll go through. So if we look at magnesium, we're on the third energy level, so period 3. So we go from 1s to 2s to 2p to 3s. And we're in that second group, so we're only in the s, so we're only going to go as far as 3s. And magnesium has 12 electrons, so we're going to fill it with 12 electrons, which go 2, 4, 6, 8, 10, 12 electrons. So that's what magnesium should look like. And if you write it out as an expanded electron configuration, you get 1s2, 2s2, 2p6, 3s2, which has a total of 2 plus 2 is 4 plus 6 is 10 plus 2 is 12 electrons. Now, take a moment and do that for oxygen. And when you we see that oxygen is in period 2, and it is in that p block, so we're going to go all the way to 2p. Now oxygen has 8 electrons, so when we fill it, we're going to fill in 1, 2, 3, 4, 5, 6, 7, 8. So we're going to go and we're going to spin pair one of the 2p orbitals, but we're going to fill the rest first before we spin pair it. And if we write that as an expansion, it's going to be 1s2, 2s2, and then 2p4, which is 2 plus 2 is 4 plus 4 is 8 electrons. So now I want you to try arsenic. Arsenic, and try that. Now if you do arsenic, arsenic is on the 4th energy level, and it's all the way over into the p block, so we're going to go from 4s through 3d all the way to 4p. Arsenic has 33 electrons, so we're going to have to fill that with 33 electrons, which actually creates a partially filled 4p orbital. And that's going to be 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p3. And let's try it for silicon. Silicon is on the 3rd energy level all the way over in p, so we go 1s2, 2s, 2p, 3s, 3p, and silicon only has 14 electrons, so we're going to fill accordingly. And you should have 1s2, 2s2, 2p6, 3s2, 3p2. Okay, so not too bad. This actually should hopefully feel a little bit better than quantum numbers. It's a little bit more understandable, and we're going to do a lot of practice tomorrow on it. So I will see you then. Oh, good. I still don't know how to pause this. There we go. Bye, guys.